All right, welcome to learning target number 8, where we're going to discuss Hess's Law. This learning target will cover how to calculate the overall enthalpy change of a chemical process regardless of a reaction pathway. So let's define what we mean by Hess's Law. Hess's Law, named after Germain Henry Hess, states that the overall energy change in a chemical reaction depends only upon the initial and final enthalpy values in a system and are independent of the reaction pathway. So what do we mean by that? So here's a reaction pathway. We're going to say that reactant A is going to go to product B. But this might take a while. It might go through many steps. So instead of A going directly to B, A will react to make C first, and then C will react to make B. Each one of those steps has an enthalpy of formation or an enthalpy of reaction attached to it. So what we can say here is, since A goes to C and then C goes to B, that the overall enthalpy change in the reaction will be the enthalpy changes in those two steps. I stated that here as well. So if A goes to B, but it does so through the pathway of A to C, then C to B, then the enthalpy change of A to C plus the enthalpy change of C to B will give you the overall enthalpy change of the reaction. So let's make this a little bit more specific by looking at one particular case. Let's look at graphite, which is pure carbon, turning into carbon monoxide. So graphite will eventually react with oxygen to create carbon monoxide gas. But this is an incredibly slow process, probably because I've got carbon, which is one of the most strongest lattice structures in the world, reacting with oxygen incredibly slowly to make a mole of carbon monoxide gas. So I've got solid added to gas to make a gas. So it's going to be a pretty slow process. And so it happens in steps. Here's the steps in which it's going to occur. I'm going to have my carbon reacting to oxygen first, but the first thing I'm going to make is carbon dioxide. And that's going to have an enthalpy of formation where I'm going to release 393.5 kilojoules of heat when this reaction happens. And then when I have enough carbon dioxide and I double the quantity here, the carbon dioxide will decompose to make your carbon monoxide and oxygen gas again. So when that occurs, the heat of reaction, or how much heat will release when the carbon dioxide decomposes, is negative 566.0 kilojoules worth of energy. So we need to know a couple of rules that go along with this process in order to understand how these two reactions will end up being this reaction here. Here are these rules. Rule number 1, when a reaction is reversed, so is the sign of the enthalpy. So here's my carbon making carbon dioxide again. So the heat of formation here is going to be negative 393.5 kilojoules. But if I was to reverse this process and all of a sudden the carbon dioxide decomposes to make carbon and oxygen, my heat of reaction is now going to be positive. So if I flip the equation, I flip the sign of the enthalpy. It turns in from an exothermic process to form carbon dioxide to an endothermic process to break down that carbon dioxide to make carbon and oxygen. Rule number 2. When molar quantities of reactants and products are increased, the enthalpy increases proportionally. I could also say when the molar quantities of reactants and products are decreased, the enthalpy also decreases proportionally. And let's see what we mean by that. Here is my carbon reacting with oxygen to make my carbon dioxide, and I've doubled the number of moles involved here. So if I double the number of moles of carbon, double the number of moles of oxygen to double the amount of carbon dioxide, I will double the enthalpy of formation. So 2 times negative 393.5 turns into negative 787 kilojoules for the heat of formation when carbon turns into carbon dioxide, doubling the molar quantities. All right, so now we have our rules in place. Let's use those two equations to make some carbon monoxide. Okay, so our goal is to create carbon monoxide from its elements, carbon and oxygen. And I've already mentioned it takes 2 steps to get there. You make your carbon dioxide first, and then the carbon dioxide decomposes into make carbon monoxide. So I'm going to say that my goal of making carbon monoxide is going to be my goal equation. When I use Hess's Law terminology, the goal of the overall reaction that I'm trying to calculate the enthalpy change, I call that the goal equation. Then what I'm going to do here is I'm going to use my equations that are involved in my steps and figure out what I need to do to the enthalpies in order to get the overall enthalpy of my goal equation. So in my goal equation, I notice I've got 2 moles of carbon. Well, in the first step here, I'm making carbon dioxide from 1 mole of carbon. So what I'm going to do here is I'm going to take that first equation, carbon plus oxygen gas, to make carbon dioxide, and I'm going to double everything, kind of like we just did in the previous example. And I'm going to double that, double that, double that. And so I'm going to double the enthalpy of formation of that carbon dioxide. 393.5 times 2 makes the, let me just double check my math really fast. 393.5 times 2, that negative 787, like you saw on the last screen, kilojoules. All right, so this takes care of this carbon. So I'm going to check that one off because I've got the carbon here. Now, I have the oxygen on the left side already. I have too much oxygen, but I'm just going to leave that oxygen alone for a second and focus on the carbon monoxide. So the carbon monoxide, I look at what equation contains carbon monoxide, and it's the second one. And it contains the correct quantity. So I'm just going to copy down that reaction again, that bottom reaction. So I have 2 CO2 will make 2 COs plus O2. And I did nothing to the enthalpy of that equation. So I'm going to just say that my enthalpy is going to be the negative 566 kilojoules. Let's, for all intensive purposes today, pretend all of these enthalpy of formations are literature values. All right, so those are my step equations to make my goal equation. So I'm going to see if these 2 equations add up to make my goal. Well, I've got 2 CO2s on the left, 2 CO2s on the right, and so I get to cancel those out. I get 2 O2s on the left side, 1 O2 on the right side. So the one on the right side cancels out, and the one on the left side reduces to 1. And now I'm left with the correct equation. 2 C's plus O2 makes 2 COs. So that's just a double check to make sure I made my goal equation, which I did. And so I figured out the correct configuration of enthalpies of formation and decomposition that we'll add together. So then I'm going to say, all right, negative 787 plus a negative 566 is going to get me negative 1,353 kilojoules to form carbon monoxide from its elements. So that is a simple Hess's Law problem where I used the equations involved in each step to come up with the overall goal equation. Use the enthalpies of formation that's tied to each step equation, figure out what to do with those enthalpies in order to get the overall enthalpy of formation. And in this case, I multiplied the enthalpy of the first step by 2. Okay. In the next video, you're going to see this taken up to the next level, where you're going to find the enthalpy of formation of methane from the enthalpy of combustion data that you'll get in your data booklet. Hang on tight.